5, 4, 3, 2, 1, top.
My future as a scientist depended on that launch. It's a huge collaboration, Planck, that involves Europe, United States.
The Planck telescope was launched by the European Space Agency in 2009. Its aim to study the early history of the universe.
So the Planck satellite is about 1 million miles away from the Earth at the moment, following the Earth around the Sun. We can keep our satellite looking away from the Earth and the Sun, and it will just stay looking away from the Earth and the Sun as it gets pulled around the Sun by the Earth.
Planck scans around and builds up a picture of the sky, does it in a very broad swathe like that. And in 6 months, as the Earth goes around the Sun, Planck builds up a picture of the whole sky. So it covers once every 6 months. So in a year you cover the sky twice.
The Planck telescope captures an image of the visible flash that occurred in the young universe, when matter as we know it came into existence. It is remarkable that it is possible to view an event that occurred billions of years ago.
Because of Einstein's theory of relativity, we have the idea that the speed of light is finite. So that means the further away something is, the longer it takes the light to get to us. So as we look at things that are further and further away, we see the things further and further back in time. So we basically are enabled to see the universe really long ago and really when it's really, really young. And the cosmic microwave background is like the oldest light that we can see.
It shows the image of the cosmic microwave. Now before, in the other images you saw the galaxy lying across the centre of the image. Now that's been removed here. If you were to look out into the sky and see the cosmic microwave background alone, if there was nothing else in the universe, you'd see something which is very, very uniform. You see with microwave eyes, you'd see something that's very uniform. But on top of that background, there are very, very tiny ripples. And these are the things that are shown in this image here. So red is where the light, the temperature of this radiation is slightly hotter, and blue is where it's slightly colder. We're talking of a minuscule amount here. It's 1 part in 100,000. And it's the relative proportion of these ripples which tell us about how much ordinary matter there is in the universe, how much dark matter there is, how much dark energy there is, and how fast the universe is expanding.
But the most important results from Planck are the evidence that the fluctuations that we see were generated during an early phase where the universe went through very, very rapid expansion. We call that an inflationary phase. So, the fact that the Planck results agree extremely well with the predictions of inflationary models of the generation and evolution of fluctuations, I think is strong evidence that something like that actually happened.
But this isn't the end of the process. Now, this is only part of our data. We've still got another half of our data to go. We will make next year. We're going to make a better map. And also we're going to analyse the polarisation, which hasn't been talked about at all in this time round. We're a step further along the way here in order to to find out where we came from and where we're going.